Good morning, students. Today I shall start the part 3 of this chapter, Rotational Spectroscopy. So, after the second part, the third part starts from this topic. Substitution effect on rotational spectra. That is, if we substitute an atom of a molecule by its some isotope, then what will be the effect of its effect on the rotational spectra? What are the changes which will take place in the spectrum? We have to discuss here. So, rotational spectra, this fact has been established. For example, if we take the example of carbon monoxide molecule, in which carbon is normal, that is C12, and if we take the isotope of carbon, that is C13, then this is the another carbon monoxide molecule. Similarly, if we take molecule HCl, here H is if replaced by its isotope deuterium, which is written by D, then this DCl will be different from HCl. Now we have to see what changes take place and how it takes place when an atom of a molecule is replaced by, or you can say substituted by, its isotope. So the fact is, which should be noted here, distribution of electron does not change. If we take carbon monoxide with normal carbon atom, and if we take carbon monoxide with C13 carbon atom, then the fact is distribution of electron does not change. That is, distribution of electron remains the same, because the number of electrons is not going to change. What is changing? It is only the mass. So, again, next property will be internuclear distance does not change due to isotope. Also, when substitution is taking place by an isotope, then internuclear distance will also not change. But mass will change definitely, because we know that isotopes are the atoms of same element with different atomic masses. Here atomic mass of carbon is 12, here atomic mass of carbon is 13, here atomic mass of hydrogen is 1, and atomic mass of deuterium is 2. So definitely mass will be changed, and reduced mass is related with this formula M1 M2 by M1 plus M2. Therefore, reduced mass will also change. Since reduced mass mu is changed and mu is related with moment of inertia with this formula, I is equal to mu r square. Therefore, definitely I, that is moment of inertia, will change. And moment of inertia is related with the rotational constant B. So, when moment of inertia changes, there will also be a change in rotational constant B. And this B is related with spacing, because we know that spacing in rotational spectra is equal to 2b. So when the value of b changes, the value of 2b changes, and hence the spacing will change. So what will happen? In the normal case, the frequency in terms of wave number for rotational spectra, we have calculated in our previous lectures as mu bar is equal to Bj into j plus 1 per centimeter. So, if B is changing, that is spacing is changing, then definitely, if spacing is changing, that is 2B is changing, then B will change, and if B will change, then the frequency mu bar in terms of wave number will also change. So, in short, we can write this type of explanation. If heavier atom is substituted, suppose we take deuterium in place of hydrogen in case of a Cl molecule, then what happens? Its mass is changing. Mass is changing means mass is increased. Mass of hydrogen atom is 1, whereas the mass of deuterium is 2. So mass is increased, denoted by upward arrow, and when mass is increased, I will also increase, because I is equal to mu r square, and mu is related with this formula, reduced mass, and therefore B is decreased, because this B is inversely related with this I. So what will happen? The net result will be spacing decreases. Since B is decreasing, therefore 2B will be decreasing, and therefore spacing will decrease, and the result will be the spectrum will be closely packed. Suppose, let us see the figure. Here the upper figure is for the spectrum of carbon monoxide, in which carbon is normal carbon atom C12, and the lower figure is of spectrum of carbon monoxide with substitution of C13 atom. So what here we are observing, that there is shifting of spectral lines towards lower region. Suppose mu bar increases. So what happens? These spectral lines are condensing or coming close together towards the lower value of the nu bar. So this is very clear from the figure, that in case of the original atom CO, and when compared with the substituted C13 carbon atom of CO molecule, there is a compact structure, there is a compact lines of spectra. Now from data it is also confirmed, which is established fact, that this has been derived experimentally. In case of carbon monoxide with normal C12 atom, the spacing, that is 2B value, is calculated to be 3.842 per centimeter. But when the same spacing is calculated with molecule carbon monoxide with substituted C13 atom, then this 2B value, that is spacing, comes out to be 3.673 per centimeter. Clearly there is a decrease in the value of spacing, and hence there is decrease in the value of B. Now a very simple question in the form of numerical is given here. Calculate the atomic mass of C13 atom. Calculate the mass of C13 atom with the help of rotational spectroscopy. We have to use the principles of rotational spectroscopy, and we have to calculate the atomic mass of C13 atom. And for this we have given B value, not spacing. Spacing is equal to 2B, but the B value is given for normal CO molecule is 1.9 to 118 per centimeter, and for the substituted C13 atom in carbon monoxide molecule, the V value is given as 1.83669 per centimeter. Mass of carbon, in case of normal, it is 12, and mass of oxygen atom of normal oxygen atom is 15.994. We can take this value as 16 also, but in the calculation the exact value has been taken 15.994. So how we start the answering of this question? We have to calculate the atomic mass of C13 atom, that is the substituted atom. What will be the mass of the substituted atom if we take C13 in carbon monoxide molecule? So we know the value of B is written as H by 8 pi square IC, where the terms are of usual values. H is the Planck constant, I is the moment of inertia, and C is the velocity of light. So if this V value is written for carbon monoxide, we write this one, and if the V value is written for carbon monoxide with substituted C13 atom, then a prime or a dash is written. So V dash is equal to H by 8 pi square I prime C, because 8 is constant, pi is constant, C is constant, but I, that is moment of inertia, is not constant, because when mass is changed, moment of inertia is changed. So the only change in this expression will be I, that is moment of inertia. Now if we take the ratio of B and B prime, then the similar terms cancel out each other, and we get B by B prime is equal to I prime by I. So I prime by I is equal to B by B prime is equal to how much? We get the value, if you put the value of B normal and B prime, then we get 1.046. 1.046. Now we know the formula, I is equal to mu r square. So for normal molecule, the same formula will be written, I is equal to mu r square, but for the substituted carbon atom, we can write I prime is equal to mu prime r square. And again, if we take the ratio of I and I prime, then we get only, because r square is cancelled out, it becomes mu by mu prime. Or if we change numerator with denominator, then this becomes I prime by I is equal to mu prime by mu, which here it is calculated value. So this is equal to 1.046. Now reduced mass is mu is equal to m1 m2 divided by m1 plus m2. Therefore for normal molecule, if you calculate the value of reduced mass, then m, that is mass, is equal to mass m1 into m2, that is product of masses of the two atoms, that is C and O. So the normal carbon atom mass is 12, and the normal oxygen atom has mass 15.994. So m1 into m1 by m1 plus m1 into m2 divided by m1 plus m2. Similarly, mu prime, if you calculate, then here we have to calculate the value of mass of C13 carbon atom. So here we have written m into 15.99, which is the mass of oxygen atom, divided by m prime plus 15.994, which is also, here it is multiplication sign, here it is addition sign. Now if we take the ratio of mu and mu prime, then we take here the two expression like this, and when calculated it comes as 1.046. Here mu prime by mu is equal to this term divided by this term. So here the expression will be like this, and this mu prime by mu has already been calculated as 1.046. So it is equal to 1.046. So when this is calculated, this will give the value of m prime is equal to 13.007, and this is the mass of the substituted C13 atom. So C13 means the whole number is 13 and the fraction is 0.0007. So we can write C13 as usual. Non-rigid rotator. This is also called as rotor, but in general it is called as rotator, because the molecule when rotates, it gives the rotational, it is due to the rotational energy, and the rotational spectrum is obtained. Here we can say that bond length is constant only at lower value of G. Just in the beginning of this chapter, I have explained what is the meaning of this rotator, rigid rotator or non-rigid rotator. A rigid rotator means the distance between the nuclei of the two atoms in a diatomic molecule, that is bond length, should be constant. So in case of rigid rotator, the distance between the nuclei of the two atoms of the diatomic molecule, that is the bond length, should be constant, and then it will be called as rigid rotator. So once we have assumed that the distance between the two atoms in a diatomic molecule is always constant, but it is not so. This bond length is constant only at lower value of J. Lower value of J means there are so many rotational lines or rotational energy levels. J is equal to 0, J is equal to 1, J is equal to 2, J is equal to 3, J is equal to 4, J is equal to 5. So there are so many rotational energy levels. So when the energy is in the lowest energy level, so when the energy in the lowest state, that is J is equal to 0 or J is equal to 1, then only this condition is fulfilled. But when energy increases, that is, if we go to higher energy levels, higher rotational energy levels, that is J is equal to 3, J is equal to 4, J is equal to 5, then this condition is not fulfilled. Because here we can also see from the simple example. Suppose this is a diatomic molecule. There are two atoms and this is the bond length, and this is rotating. If the rotation is slow, then these energy levels are related with these rotations. But when this rotation speeds up, very quickly it is rotating, then the rotational energy levels are in these energy levels, and in that case what happens, the bond length which we have considered as constant, it stretches like a spring, and the condition rigid rotator is not valid. The condition rigid rotator is valid only in case of lower rotational energy level, that is when the rotation is slow. But when the rotation is fast, then there is a stretching in the bond length, and the character rigid rotator is not fulfilled or it is not valid. And in this case means when the rotation is fast and bond length is not constant, then it is called as non-rigid rotator. So from figure here, we have also shown that if this is a rigid rotator, these are the two atoms of a rigid rotator, and here R is the bond length, and the value of J is very small, that is lower value of J. When the rotation becomes high, that is we go up to the higher rotational energy levels, then this bond length stretches and the value of R is increased. So when value of R is increased, then I is related with formula I is equal to mu R square. So I is directly proportional with R, therefore I also increases. Since I and R are directly proportional to each other, so when R increases, I also increases. And the rotational constant B is related with I with this formula, that is I is inversely proportional with B, and when I increasing, then B decreases. And B is related with spacing. B is related with spacing that is 2B. So when B is decreasing, spacing will also decrease, is going to decrease. Spacing is also going to decrease. So if we see this formula, if we see this figure, this is the normal case. J is equal to 0, J is equal to 1, J is equal to 2, 3, 4, 5 and 6 and other, such that. So for a rigid rotator and for non-rigid rotator, the situation is like this. That is, here 2B value is, here 2B value, here 2B value is less than the case of rigid rotator. Now, rigid rotator is only an approximation and cannot be regarded as a true picture of a real molecule, because in case of actual case, in what happens that there is always rotation of the molecule depending upon the temperature or other factors. So the concept of rigid rotator is only an ideal, and it is not showing the real picture of the molecule. So actual picture of the molecule is non-rigid character. So due to non-rigid character, the elastic bond may have some vibrational energy, because we have just explained that when this molecule is rotating fast, then what happens? The bond stretches, and when its motion becomes slow, then again it compresses. So there is a compression and expansion. There is compression and expansion as the rotation is fast and slow. As the rotation is fast and slow, so there is a compression and expansion. That is, a vibration is set up. Here we have discussing the rotational spectra, but in this case we have introduced the term vibrational energy also, because the vibration is also set up in this case. So due to vibration in the diatomic molecule, when the character is non-rigid rotator, the bond length and rotational constant vary, and hence wave number nu bar is changed according to the formula. This part is only for the rigid rotator. B into J plus 1 is for the rigid rotator. But when the character becomes non-rigid rotator, this additional term is introduced. The additional term is minus dj square into j plus 1 whole square, where j is the rotational quantum number and d is the centrifugal distortion constant, and the value of d, that is centrifugal distortion constant, is 4b cube divided by omega square, where omega is the angular frequency, b is the rotational constant, and the value of omega is 1 by twice pi under root k by mu. Mu is the reduced mass, and k is the force constant. So the selection rule for the non-rigid rotator is same as in case of rigid rotator, that is delta j is equal to plus minus 1. So transition takes place in the adjacent energy level, one energy level in case of upward, or in case of in upward case, or in downward case. Now the transition, if transition takes place from j to j plus 1, that is if transition is taking place this one, j to j plus 1, if this transition is taking place, then we have formula like this. We have formula nu bar is equal to dj into j plus 1 minus dj square into j plus 1 whole square. So if we put this formula for this transition, that is the transition from j to j plus 1, here it is written j to j plus 1, then this whole is written for j plus 1. So in place of j we have written j plus 1, in place of j plus 1 we have written j plus 2. Here for j we have written j plus 1, and for j plus 1 I have written j plus 2. Now after this minus sign, because we have to subtract the value from the upper energy of upper energy level to the lower energy level. So again we have to write this one, and in this case here it is j, so we have written j, again j and j plus 1. Now we have to simplify this, and for simplifying similar terms are taken together. So this one and this one are taken together, and this and these two terms are taken together. Now we have taken some common, and the final expression becomes like this. So in the final expression, which is this one, the value is 2bj plus 1, which is just similar to the previous one when a transition takes place from j to j plus 1. We have calculated in previous lectures that when a transition takes place, in case of a rigid rotator, the value becomes from energy level j to energy level j plus 1, then it is 2bj plus 1. So this is the only extra term when we calculate for the expression in case of non-rigid rotator. That is, the spectrum of non-rigid rotator is almost similar to that of the rigid rotator molecule, except that each spectral line will undergo a displacement towards the low frequency value, because here it is minus sign. So some value will be subtracted. The value will have lower value than when compared with the rigid rotator. Suppose we have a spectrum of rigid rotator like this, where the spacing is 2b, here it is also 2b, and when it is compared with the spectrum of non-rigid rotator, then what we are seeing here, there are two types of there are two reasons in this figure we have observed. In the first three lines, we see that spacing is almost constant, whereas after the first three lines, there is decrease in the spacing, which is very clear from this figure. So spacing is constant at the lower value of j, but for higher value of j, the spacing decreases at the j value is increasing. Here I have written nu bar is increasing from left hand side to right hand side. So this is the effect of when a rigid character changes into a non-rigid character. Now these are some questions for practice. Which of the following molecules are microwave active? Which of the following molecules are microwave active? So for answering these questions, we have to keep the following facts in mind. What are these facts? Dipole moment should not be zero. Dipole moment should not be zero. Perfect molecules are microwave inactive. Perfect molecule means atoms attached with central atom must be same and should not contain any lone pair. So that is the concept of perfect molecule. For example, in sp hybridized molecule, this acetylene molecule is the perfect molecule because hydrogen atoms are attached on both sides. Also, carbon dioxide nitrogen on both sides. Also carbon dioxide, nitrogens are inactive. In sp2 hybridization, this ethylene molecule is perfect molecule and it is inactive. This BF3 molecule is perfect molecule and is active. In sp3 hybridization, methane molecule is perfect molecule and this is also inactive. Here answer is given, which one is active and which one is inactive, and these are the facts on which we decide which molecule will be active. Active means microwave active and microwave inactive, that is it will give rotational spectra or not. So answer is given and these are the facts from which we can decide. Okay, thank you very much.